Video 18-3, Solubility Equilibrium. So, first thing we look at, something called a solubility product. Okay. Now, some ionic solids are going to be really soluble in water, so you put them in water and they totally ionize, or dissociate rather, into the ions X plus and Y minus. The arrow only goes in one direction. Okay. Now, even though we say some of these things are insoluble, okay, they actually do dissolve to a really small degree. Okay, and the reason why they stop dissolving is the solution becomes saturated, okay, which means that the saturation level for this is a really low level. Okay, so for example, silver chloride, this is one of those things that was considered to be insoluble, okay, but it does dissociate to a small part into Ag plus and Cl minus ions. Okay, so now, because we have an equilibrium, we can write this as a reversible reaction. Okay, so we can write out an equilibrium expression for it. And don't forget, it's the products over the reactants raised to the coefficients. Okay, so to the first power and to the first power, and you do not put in solids or liquid. So in our KEQ, those don't show up. Okay, now this KEQ we give a special name, and we call it KSP, and the SP stands for the solubility product. Okay, so it's a solubility product constant, and this basically tells you how much of the substance can actually dissolve, okay, to a certain degree. Now, these values are going to be really small. Why? Because take a look at the equation. How much Ag plus and Cl minus do you end up with? These are really small numbers. Multiply them together, you get even smaller numbers. Okay, and you can find the values for different substances, their KSPs, in table 18-3 in the book, page 579. Okay, now, how do you find the solubility of an insoluble solid? Okay, it sounds weird, but remember, there really is no insoluble solid. Okay, so how do you figure out how much of it will actually dissolve? Okay, don't forget, solubility is the maximum amount of solid that can dissolve in a given amount of solution. Okay, and the units are in molarity, moles per liter. Okay, so let's use what we just learned. Find the solubility of AgCl. The KSP, if we look up in the table, 3.8 times 10 to the negative 11th. Okay, now don't forget, this stuff breaks up, so we write our KEQ, which is now our KSP equation, okay, Ag plus times Cl minus. Okay, now S is the amount that dissolves. Okay, if 1 mole dissolved, you get 1 mole of Ag plus and 1 mole of Cl minus. Okay, but how much of the Ag plus will you get? In terms of S, you'll get S because it's a 1-to-1 ratio. How much Cl minus will you get? The same amount. Okay, so we can say then that the concentration of Ag plus is equal to S, and the concentration of the Cl minus is also going to be equal to S. Okay, so from that, we can plug those in. Okay, S is the solubility of the AgCl. So both of these are going to be equal to each other, and they will also be equal to S, because whatever dissolves of the AgCl has to turn into Ag plus, and also it's going to be same as the Cl minus, because it's a 1-to-1 mole ratio. Okay, so substituting in, our S is for the Ag plus and the Cl minus. Okay, we get S times S is equal to the KSP. So S is equal to, which is basically S squared, right? So S is equal to the square root, or KSP to the 1/2. Okay, so all you need to do then is take the square root of 3.8 times 10 to the negative 11th, and that will give you the solubility. Okay, and that should come out to be 6.2 times 10 to the negative 6. Now what's the unit? Solubility is the amount that dissolves in moles per liter. So the molarity, or the solubility, is 6.2 times 10 to the negative 6 moles per liter of AgCl that can dissolve. Okay, what will the Ag plus concentration be? It will also be that, because this is also equal to the Ag plus concentration, and it's also going to be the Cl minus concentration. Okay, watch out for common ion problems. What happens if I have AgCl and I dump in some more Cl minus? Okay, well, it pushes the equilibrium this way. But don't forget, this amount still has to adjust so that Ag plus times the CO minus is still going to be equal to the KSP amount. Okay, try another one. Now, is it always going to just be equal to the square root of the KSP? Okay, well, let's try this one. What happens when we put FeOH2 into solution? Okay, FeOH2 breaks up into our ions. It's Fe2 plus, you can tell from the formula, plus OH minus, and then balance it with 2. Okay, now what's the problem? Okay, S is the amount that dissolves. So what is the Fe2 plus concentration going to be equal to? Well, if S moles dissolves, it's a 1-to-1 ratio, so you'll also get S moles per liter of Fe2 plus. Okay, but what happens to the OH minus concentration? It's 1 mole producing 2 moles. So if S dissolves, you're going to get 2S. Okay, write these things out. This will prevent you from making stupid mistakes. Okay, now, next thing, don't get lazy. You skip this part. This is where you make mistakes. Okay, so write out the KSP equation. It's equal to the Fe2 plus concentration times the OH minus concentration. Remember, you never put this coefficient inside. The coefficient becomes an exponent. Okay, now look and see what you have. Fe is equal to S. OH minus is equal to 2S. Then it says to square it. Okay, which means the KSP is equal to S times 4S squared, which means that's equal to 4S cubed. Okay, so how do you solve this? S is equal to, move the 4 over to the other side, KSP over 4, but that's equal to S cubed. Okay, so what do? S is equal to the cubed root of KSP over 4. Or, if you don't know how to do that on your calculator, it's KSP over 4 to the 1/3 power. Okay, and be careful when you plug these numbers in. Make sure you calculate this part first, push equals, and then take the cube root or raise it to the 1/3 power. Okay, so when you look up where the KSP of the FeOH2 is given to you there, so that means S is equal to KSP 8.0 times 10 to the negative 16th, divide by 4, and then raise the whole thing to the 1/3 power. And you should come out with 5.8 times 10 to the negative 6th. And its solubility, so that's the molarity. Okay, what are the concentrations of Fe plus and OH minus? Fe plus will be this concentration. OH minus will be twice as much. Okay, now precipitation reactions. Okay, it's possible that you can put 2 ions together and not get a precipitate. Okay, you get a precipitate if the concentration of the ions involved in the reaction exceeds the KSP. Okay, then a precipitate will form. Okay, now Q is something known as the ion product. What's the Q equation? It's exactly the same as the KSP. Okay, now how can you tell for precipitate forms? If Q is greater than the KSP, then a precipitation reaction will occur when you mix the 2 solutions together. Okay, now to determine if a precipitate will form, first thing, write out the formula for the precipitate that could form. In other words, it's a double replacement reaction. Write out the reaction, figure out which is the precipitate. Okay, next thing, from that precipitate, write out the KSP equation. Okay, next thing, figure out the concentration of the ions that are involved in the KSP equation and watch out for dilutions. Don't forget, when you mix 2 solutions together, the concentrations that you started with are not going to be the same as the concentrations after they're mixed. Okay, next thing, calculate Q, and don't forget the Q is the exact same as the KSP formula, so just plug in the values into the KSP equation. Okay, Then the last thing, compare Q with the KSP. Okay, and the KSP for the precipitate you have to look up in the table. Okay, so let's try one. Figure out if you're going to get a precipitate when you use 755 mLs of 0.025 molar silver nitrate and you mix it with 2.500 liters of 3.45 times 10 to the negative 5th solution of sodium carbonate. Okay, so what are the steps? First thing, figure out what's the precipitate that's possible. So our reaction is going to be, let's see, silver nitrate, AgNO3, plus sodium carbonate, which is Na2CO3. Okay, what are we going to get? Silver reacts with the carbonate, and that will give you Ag2CO3. Make sure you break it up and find your proper charges. Carbonate's 2 minus, Ag's 1 plus. Okay, and sodium goes with the nitrate, and that's going to be NaNO3. Okay, so now what you need to figure out, what's the K, which one's the precipitate? Okay, all the nitrates are soluble, so that's your precipitate. Okay, next, write out the Q equation for it. Okay, so you need to take the precipitate, Ag2CO3, break it up. Okay, that'll break up into Ag plus and CO3 2 minus. Okay, and then balance it. You need 2 of those. Okay, next thing, we're going to write out the Q equation, which would be the exact same as the KSP equation. So Q would be equal to concentration of the ions, the products, Ag plus times raised to the coefficient squared times the CO3 2 minus concentration. Okay, now this is not a solubility, so you're not going to do the S thing. Okay, so do not do the S thing. We need to figure out next what's the concentration of Ag plus and what's the concentration of the CO3 2 minus after you mix them. Okay, so next step, figure out the concentration of each ion. Okay, silver nitrate, AgNO3, will produce Ag plus and NO3 minus. Okay, it's a 1 to 1 to 1 mole ratio. This concentration was 0.0250 molar. Okay, so before you mix the two solutions, the silver concentration, which is the only one we're worried about, will also be 0.0250 molar. Okay, and the second one is we're worried about what's the carbonate concentration, because that's the other thing that made our precipitate. So sodium carbonate, Na2CO3, breaks up into Na plus and CO3 2 minus. You need 2 sodiums, but we're only concerned about the carbonate. Okay, so it's a 1 to 1 ratio also. So since the sodium carbonate was 3.45 times 10 to the negative 5th, the carbonate will also be the same concentration. Okay, now that's before we mix it. So what is the carbonate concentration after we mix it? Okay, don't forget you're going to use M1 times L1 equals M2 times L2 to figure out the concentrations. M2 is our new concentration that we're looking for. Okay, so what was the carbonate concentration before we started? It was that. Okay, 3.45 times 10 to the negative 5th times the volume, 2.5000 liters. Okay, and it's going to be equal to M2, which is what I'm looking for. L2 is the total volume. It's going to be that plus the 755 mLs, okay, which is basically 0.755 liters. So add that together. So L2 is going to come out to be, let's see, 3.255 liters. Okay, so what's our new molarity going to be for the carbonate? M2 is going to be 2.65 times 10 to the negative 5th molar. Okay, now we do the same thing for the Ag+. Okay, what's our Ag+ concentration? It's going to be equal to, again, basically we're solving for M2, which is going to be equal to M1 times L1 divided by, L2. Okay, M1 is 0.0250 molar. L1, we want to use it in liters, so it's going to be 0.755 liters, and divide by the total volume, which is the same as down there, 3.255 liters. Okay, and that'll come out to be 5.80 times 10 to the negative third molar. Okay, so that's our new Ag+, that's our new CO3 2- concentration. Okay, last step, find Q and figure out if it's greater than the KSP. Okay, don't forget the Q equation was equal to concentration of Ag+ squared times the concentration of CO3 2-. Okay, and we just saw that Ag+ concentration was, let's go take a look, 5.80 times 10 to the negative third. Okay, and don't forget, it says take that concentration and square it. Okay, times the carbonate concentration, which was down here, 6.25 times 10 to the negative fifth. Okay, and calculate what that comes out to be. And that should come out to be 2.10 times 10 to the negative 9th. Okay, now what do I do with that value? Well, I need to go look up what's a KSP value for silver carbonate, Ag2CO3. Okay, look that up in the book, and the KSP, when you look it up in the book, is 8.1 times 10 to the negative 12th. Oops, a little hard to see, 10 to the negative 12th. Okay, so our Q value is pretty small, but the KSP is even smaller for that. So, will we get a precipitate? Yes. We get a precipitate, because even though it's pretty small, it's still larger than 10 to the negative 12th. Okay, so here's your review problem. What's the solubility of silver carbonate? Okay, this is not a Q problem. Solubility is an S problem. Okay, calculate it and answer it on the quiz.